Okay, so this is the third video about the presentation of this work, which is available in the archive. It involves a group of people from the NSF CCI, the center that is led by Victor Batista from Yale University. So in the first video, we explain what we mean by spectral kissing. In the second video, we explain what squeeze Kerr-nonlinear oscillator refers to, and we found this Hamiltonian. And so this is the Kerr-nonlinearity, this is the squeezing amplitude, this is the effective Hamiltonian that describes the system. And now we are going to move from here. We are going to analyze this Hamiltonian. In this third video, we'll be talking about the spectrum of this Hamiltonian and the eigenstates of this Hamiltonian. Okay, so in this experimental work, the group of Deborah studied the spectrum of this Hamiltonian as a function of this ratio, squeezing divided by Kerr. And what do we see in this figure? If you look at it, you will see what? Kissing, no? The merging of two adjacent levels, merging of two adjacent levels. What is this? The excited state quantum phase transition. Yes, here also, if we extrapolate, we see that the kissing will be happening. Now, so you can see here in the theoretical result. So this is a Hamiltonian that clearly presents an excited state quantum phase transition. So what is exciting here is that with this experiment, we have direct access to the spectrum. And so we have now a platform to study excited state quantum phase transitions. But what is even more special is that with this experiment, with this platform, they can do not just frequency time, not just frequency domain measurements, but as time domain measurements. And so they can study not only the spectrum as we saw in this figure, but they can also study dynamics. So they can study the consequences of the presence of the ESQPT, what is going to happen in the dynamics. I'm going to mention some of these features, which will be discussed in other videos. Okay, in this video, as I said, we'll be talking about spectrum and eigenstates, but what will come next, what are the dynamical consequences of the presence of ESQPT? One of them is exponential growth or of out-of-time order correlators. And this happens because of instability. Another consequence is the slow evolution of the survival probability for the state that has energy at the ESQPT. So the survival probability, which is this overlap here, decays lower for this state than for other states. Sounds a little bit like a paradox, a fast evolution of auto, slow evolution of the survival probability, but you will see that we resolve this apparent paradox very easily when we see the classical limit of the system, which will also be coming in the next slides, in the next videos. But let's then move to the spectrum. So this is the Hamiltonian, the effective Hamiltonian that is studied experimentally. We'll be dealing with this one where we divided everything by the Kerr. So this ratio here is our control parameter. So this is the result from the experiment. They don't have many levels here, but theoretically we can have many more by going into larger values of the control parameter. And this figure is very similar to the one that we showed in the first video for the Lipkin model. Now, on this side, we have even and odd states with different values. On this side, they merge together. So right at this line, we have the kissing, we have the merging of the levels. So on this side, they become degenerate. If I show the figure for just one sector, in this case here, I'm showing the even sector, we see that there is still something special going on along this line, which is the clustering, the accumulation of the levels. So if I fix one value of the control parameter and look at all of these eigenvalues, make a histogram with all of these eigenvalues, now look at the density of states, we see this peak. This peak that is typical of excited state quantum phase transitions. Now, this nonlinearity defines what we call ESQPT. Very well. So this is what we already know about the spectrum. Now what we want to discuss is the eigenstates. There is something special happening also along this line for the eigenstates. Well, let's start looking at the ground state when C is 0. So here I'm just showing the levels from the even sector. The ground state is the Fock state 0. As we increase this control parameter, well, this ground state is going to change. But what is special is that the eigenstate that is closest, the closest one in energy to the line of the ESQPT, and to the energy of the ESQPT, that state remains very much localized, and very much localized where? In that Fock state 0. So it's as if as we increase the control parameter, we carry this Fock state along this line. It's not exactly the Fock state, but it's very close to it. How do we know that this state at the ESQPT is so much localized? Well, we study its structure. So we pick all of the eigenstates, look at each one of them, now write these eigenstates in the basis of Fock states and study these components. And that's what I'm showing here to you. So we are along this vertical line. Now, so if I select a state here below the ESQPT and I look at the components of this single eigenstate that I select as a function of the energy of the Fock states, what do I see? Many, many points, meaning that this state that I select is delocalized. It has many components, many participation, many Fock states, most of them, of course, from very low energy, because this state here has low energy. Now, if I select a state above the ESQPT, I see, again, many, many points. Now, contributions from Fock state that have low energy and high energy. Now, many, many, so delocalized state. However, if we pick an eigenstate right here, the closest one to the energy of the ESQPT, what do we see? This, an isolated point, meaning that this state is very much localized, and very much localized in which Fock state? The Fock state 0. Okay? There are quantities that we can use to measure how much spread out or how much localized the state is. One of these quantities is this one, which we call participation ratio, PR. So each eigenstate will have associated with it a value for this participation ratio. And so this participation ratio is defined as 1 over the sum of all of these components to the 4th. Okay, so if the state is delocalized, if the state has the contribution of many different Fock states, then it will have many, many tiny C's. The participation ratio will be large. That indicates delocalized state in that basis. If we have few states participating, then the participation ratio will be small. So this is what we are showing in this figure. So here we have the value of the participation ratio for each one of these eigenstates when the control parameter has this value, 180. We have this peak in the density of states at this energy. Well, at this same point, what happens to the participation ratio? A drop, indicating that the state right at the ESQPT became highly localized. Okay, so we see that the ESQPT affects the spectrum and affects also the structure of the eigenstates. And where we are going to find the explanations for the localization of the eigenstates, where we're going to find this envelope, the envelope of this density of states, where we're going to find this line that marks the ESQPT by looking at the classical limit of the system. Now, by looking at the classic counterpart of the Hamiltonian, and this is what we are going to do in the next video. So I'm stopping here. This was a short video. Next one, we are going to talk about the classical limit.